It's a pleasure to be here among so many illustrious people, some who I've known for many years, others who I've known about for many years but have never met. And it's really great to reconnect with a lot of people that I've known too. Dennis is right, I am his tormentor. We poke each other a lot through email and in person, and I say, "You plant guy, you old rascal," and he says, "Ah, you synthesis guy," and so it's kind of that thing. Anyway, I've changed the title just a little bit, but the content's the same. And what I'm going to do is show you what happens when you plant people, identify a psychedelic natural product, and give it to a chemist. And so I'm going to talk about what the chemists have done to try to exploit those as new leads, generate new molecules. You've probably heard of a lot of them. A lot of the molecules I made in my lab have become research chemicals, which you can buy on the internet, some more dangerous than others. But anyway, I'm going to give you sort of an overview of kind of the things that I have mostly done. And we're going to talk about tryptamines, phenethylamines, and ergolines, the areas I've worked in. Mostly phenethylamines and ergolines, in particular LSD. Almost no one has worked with the chemistry of LSD other than my lab for the last couple of decades. So some of these slides really need no discussion. You all know these. Teonanacatl, Aztec food of the gods, psilocybe mushrooms. And of course, all of you know that they contain these 4 oxygenated tryptamines. Now, I have to warn you, I'm going to talk about some chemistry. And I taught chemistry for many years, and I taught a review of chemistry to the pharmacy students, and whenever I would say I'm going to talk about organic chemistry, there was a collective groan from the audience. Now, I'm aware that psychologists and psychiatrists don't know any chemistry, and a lot of botanists don't really know any chemistry. But I'm sure you're a more educated group of botany-type people, so you know chemistry. Nevertheless, I will go through and try to explain things in detail so that you grasp what I'm talking about without, I put a bunch of dirty pictures up. That's what Sasha used to call them. Put a bunch of dirty pictures up. I didn't understand a word he said. So actually, if I say something that's really confusing, and if you look around and it looks like other people are confusing, raise your hand, and I will try to clarify the point. So we know that psilocybin mushrooms contain these 4 oxygenated tryptamines. So this is tryptamine, and this is the 4 position, this is the 5 position. N-dimethyl, like you see in DMT. Everybody in here knows the structure of DMT. And for psilocybin, you have this R group is a phosphate group. And when you ingest psilocybin, the phosphate is hydrolyzed by phosphatases, and it generates the hydroxy. The phosphate comes off, and you have a hydroxy. And it's actually psilocin, or as Albert Hoffman would have said, psilocin, that's actually the active species. So psilocybin is what we call a prodrug. It's not active per se, but it's activated in the body. So this is one of the templates, and I'll talk about some analogs of that. And although Schultes maybe first discovered it, the person who really popularized these mushrooms was Gordon Wasson. Here's this 1957 Life magazine, Great Adventures in the Discovery of Mushrooms That Cause Strange Visions. And we knew for a long time that there were these mushroom stones all throughout Mesoamerica, and many of them were destroyed by an over-enthusiastic Christian missionaries, shall we say. But some of them did survive, and if you looked inside the cover of Life magazine, here you saw a picture of Maria Sabina and Gordon Wasson, the amateur mycologist who went down and had a session with her. And this magazine, this story really made a lot of people aware of these mushrooms. In botanical circles, of course, there was some knowledge of them, but for Life magazine, my parents used to subscribe to Life magazine, so this is a big deal. Now, how long have they used mushrooms? I was looking through the internet and I found this thing, and I'd never heard of this. Most of you have heard of soma, this ancient Indian beverage that was supposed to give visions of paradise. There are hymns in the Rig Vedas written in praise of soma, and nobody knows what soma is. Gordon Wasson presented the case that maybe it was Amanita muscaria. But if any of you have ever tried Amanita muscaria, I haven't, but I know lots of people who have, you go, this ain't going to take you to paradise. So here's an ancient woolen embroidery that was found in a tomb. They excavated this tomb in southern China in 2009. And the tomb was from the 1st century BC to early century AD. But they say that this woolen tapestry was made much earlier. They don't actually know how it got in the tomb. And this represents a Zoroastrian scene. And because this was southern China, they think this may have been related to things that happened in India. And this priest, as they describe him, is holding a mushroom over this altar of fire. And there's some other iconographic things. There's bees and butterflies that they say signify that this was an ancient sacred ritual. Psilocybe, and they say Psilocybe cubensis. I don't know if it looks quite like that, but it could. But it's a mushroom being shared. So is it possible that psilocybin mushrooms were the magic ingredient in early soma? And I had never heard this before, so I was really intrigued by it. So it's possible. We drank the soma, we became immortal, we came to the light, we found gods. It sounds a lot like a psilocybin mushroom experience. And what about the Eleusinian mysteries? It's been a continuing Western mystery as to what the kykeon was that they drank. They know the beverage had barley and mint in it, but you were killed if you talked about the ceremony. It was a ceremony that went on in ancient Greece, as most of you know, for 2,000 years. And any ancient Greek who had been privileged to participate in this could not have ever been convicted of murder. And it was just this amazing ceremony. It's kind of like a really magnificent bar mitzvah that people could participate in. And it was done in the village of Eleusis outside Athens. We don't know anything about it, but here's a scene from the Eleusinian Mysteries. Now this is off the internet, I don't know if this is totally believable, but Persephone taking a mushroom from Demeter about the 4th century BC. Clearly there are mushrooms being exchanged here, and the Eleusinian Mysteries were somehow related to worship of Demeter. So again, we don't know what it was, but it's certainly possible that further investigation might show that the mushrooms, psilocybin mushrooms, were involved. So the history of this mushroom use goes back probably at least 2,000, 3,000 years, and maybe even further. So they've been sacred for a long time. We recently rediscovered them, but they've been around for a lot longer than what we've known about them. Now, this picture, I think, where's Donna? Is this your artwork?
No, that's from the golden guy.
Oh, no. Well, anyway, and I can't pronounce this word because I'm not a botanist, but they contain primarily bufotenin. And I've always been under the impression that bufotenin was not active, but I understand more recently that high doses of pure bufotenin are psychoactive. The effects are not particularly like psilocybin. They're not really a classic psychedelic, but they're active. And this is a major component in snuff made from the seeds of these Anadenanthera pods. Is this yours, Donna? Oh, well, sorry. Urema or Mimosa hostilis has a lot of DMT in the roots, and I have been aware of many people who've taken those roots and extracted DMT out, and it's a major source of DMT. And we all know what DMT is. And I don't need to even say anything about this. Everybody knows what this is, right? Banisteriopsis caapi, Psychoactive viridis, and of course, the mixture, the admixture boiled to make ayahuasca or huasca. And of course, DMT in the Psychoactive viridis is presumably the active species. If you don't have it in there, it doesn't really have its magic. And then I put this in because I've heard of a lot of people smoking toad venom. And this is Bufo alvaris. It secretes 5-methoxy-DMT in the parotid glands. This is 5-methoxy-dimethyltryptamine. So like psilocybin, psilocin, DMT, we've got this dimethyltryptamine structure, and we have a 5-methoxy. In my opinion, 5-methoxy-DMT is probably one of the most, if not the most potent psychedelic in terms of the effects it produces. And anyone in here who has smoked 5-methoxy-DMT would probably agree with that. Again, it's a 2-ring indole nucleus. This is called indole. It's the basis for serotonin, the tryptamines, LSD, 2 carbons away from a basic nitrogen, and N-dimethyl is what we see naturally, and a 5-methoxy. You really need either a 5-methoxy or a 4-oxygen here to get activity in these compounds to make them orally active, or to make them active. Oral activity comes with the 4-hydroxy, and I'll tell you why we think that works. So this should be an alpha beta, but I have a PC, and unfortunately Dennis uses a Mac, and my son uses a Mac, and we went through, this is the only thing that screwed up. This should be an alpha and a beta symbol, and I said, if that's all it is, Dennis, it's not a problem. So how can we modify the tryptamines? So again, this is what happens when you turn a tryptamine over to a medicinal chemist. We say, well, we got to make it more potent. We have to make it last longer. We have to improve it in some way. And I don't know that we actually do that very often, but at least we try. So there are at least a couple of places that we could talk about. Presumably, we could substitute things over here on this ring. You can't put anything over here. If you stick something here, it makes it an antagonist. It's inactive. So we could look at a 4 oxygen or a 5 oxygen. If you move anything here to the 6 or 7 position, the compounds are inactive. So there isn't really a lot of structure activity work on these tryptamines because when you start putting substituents over here, they're not active. So a 4 oxygen or a 5 oxygen for aromatic ring substitution. Also in the alpha-beta side chain positions, you could attach things here. So each of these little angles is a carbon atom with 2 hydrogens attached. And then N substitution. In the natural dimethyltryptamine, we have methyl groups, 1 carbon methyl groups. So you can modify those, and those have been modified, and I'll just comment briefly. So the problem with tryptamine or 5-methoxytryptamine or even DMT or 5-methoxy-DMT is they're broken down by monoamine oxidase in the liver. It's a reversible monoamine oxidase. You can block that deamination by attaching an alpha-methyl here. It's the same situation in amphetamine. Amphetamine is phenethylamine, which is not active with an alpha-methyl attached. And like you have dextro and levo or DNL amphetamine, you can make DNL alpha-methyltryptamine. So here we have the R isomer, and I've shown this hydrogen coming out toward you with the methyl going back, or the S isomer with the methyl coming forward and this hydrogen back. These are quite active. The S isomer that I've shown here is the most active of these two. And this is AMT, known as AMT. And this would be SAMT. The S enantiomer are more active than the R. And 5-methoxy alpha-methyltryptamine. And Sasha reported this, Sasha and I reported this years ago. We resolved it into its 2 enantiomers, and it's the S isomer that's more active than the R. And orally, this compound has a dose of around 1 to 2 milligrams. So it's quite potent and long-acting. So just some numbers I pulled out. Most of these numbers I pulled out of TCAL, Sasha's compendium of tryptamine structures. So DMT, 6 to 200 milligrams smoked, and I've just indicated it lasts up to an hour, but you know that's quite variable. It could be 20 minutes, an hour, some people 2 hours. 5-methoxy-DMT also smoked. 15 to 20 minutes is typical, but some people can stretch this out to an hour. Very potent. The dose 6 to 20 milligrams is much more potent than DMT itself. Probably 10 to 15 is a more reasonable dose. I think when I smoked it, somebody gave me 20. It was too much. And then psilocin, which is orally active, 10 to 20 milligrams, but doses have gone up to 30 or 40 milligrams. 3 to 6 hours, or 7 hours maybe. So these are orally active, these are smoked, these are smoked. Now, if you start putting larger groups on the nitrogen, it resists deamination by MAO. So if you put an isopropyl, methyl isopropyl, now this becomes orally active. You put a methyl isopropyl and 5-methoxy, it becomes orally active, PO per os. And you can do the same thing with the 4-hydroxytryptamine, and it also becomes orally active. Now you put the diisopropyl on here, diisopropyltryptamine, DIPT, it's orally active and has very weird effects. It changes your perception of pitch. So everything sounds like this if you take diisopropyltryptamine. The 5-methoxy diisopropyltryptamine is quite potent. This is an interesting compound that not many people have looked at, but diisopropyl 4-hydroxytryptamine, it's a very potent, intense compound with a fairly short action. So you can block deamination either by adding something to the side chain alpha position or by adding large alkyl groups to the nitrogen. So we asked the question, okay, DMT is not orally active, bufotenin is not orally active, but psilocin is orally active. Why is that? This is a question I asked back in 1980, and this is a paper we published. We used 360 megahertz NMR, nuclear magnetic resonance spectroscopy, and that was a high field back in those days. So we ran an NMR on DMT, bufotenin, and psilocin. Now, in an NMR, it depends upon the magnetic fields and the magnetic spins of the hydrogen atoms. So they have a characteristic absorption in the NMR that you can see as a peak in a trace. So we have 2 hydrogens here, and we have 2 hydrogens at this position. And they interact with each other, and they interact with the magnetic field in the NMR. The same thing is true here. Now, for DMT or for bufotenin, when we looked at the NMR spectrum, we could tell from the interpretation of the spectra that the side chains were twisting around, and they weren't really hindered in any way. And you could see that by the similarity of the peaks for these protons at those 2 positions. But when we looked at psilocin, they were different. They weren't equivalent. Something was happening that was keeping the side chain from spinning around. And we used a software program called, I think, Lakun 3, and we could interpret what the side chain actually looked like when we were seeing that coupling pattern. And what it looked like is that the side chain was bent back into what was called a gauche orientation, which is French for left-handed, right? Gauche. And we proposed maybe there was a hydrogen bond here. So we went ahead, we measured the basicity and the log P, the partition coefficient, of bufotenin and psilocin. Now, the pK is the pH where the nitrogen is half ionized. So at pH 9.67, at physiological pH, you have this nitrogen being protonated. Amines don't circulate through the body as free bases. They circulate as protonated forms because of the pH of the plasma, 7.4. Well, when you look at psilocin, the pK dropped to about 8.5, dropped more than a log unit lower. So psilocin is less basic. Now, this pKa depends upon the ionizability of this nitrogen, and that depends upon the pair of unshared electrons. I hope that doesn't shock anybody, but there are unshared electrons on the nitrogen, and that's why amines are basic. It's that pair of unshared electrons that makes them basic. An acid gives off a proton, a base sucks up a proton. So we've got this electron pair. Well, now, if we have an electron pair and we have hydrogen bonding to the electron pair, that's going to make this so that it doesn't have to ionize in physiological pH because it's stabilized by that hydrogen bond. Now, what's the partition coefficient? In principle, if you take a flask and you put in some octanol, which is what people use, normal octanol, it's a C8 alcohol, and some buffer, and you put in the compound, you shake it, you measure the concentration in the octanol and the water, and that approximates what happens in the body. So a log P here, and this is the log of the partition coefficient, a log P of around 3 is a drug that gets into the central nervous system pretty readily. The log P of mescaline is less than 1. The log P of bufotenin is about 1.2, but the log P of psilocin is 1.45. Now you're getting into a range where it can penetrate into the CNS. That's also important because of the ionization. If this is highly basic, it'll be solvated with water, and it can't get through the membrane if it's got water associated, so it has to desolvate. So the presence of this hydrogen bond can compensate for the lack of solvation, and so also would facilitate its partitioning into the brain. So we modeled that, and this actually, this is from a software that I use called Spartan, and it'll minimize right around so this nitrogen is right next to the hydrogen. So there is a possibility of that hydrogen bond. It's not something we just dreamed up. It actually computationally shows up. So why is psilocin active orally and bufotenin is not? A number of factors. That intramolecular hydrogen bond lowers the basicity of psilocin, so it's less protonated in plasma, and we have actually 48% of the unprotonated psilocin in plasma at pH 7.4, which is a physiological pH. Whereas for bufotenin, it's about 0.5% free base. So you have much more of the unionized free base that's necessary to partition into the brain with psilocin than you have for bufotenin. Only unionized species can partition across membranes. So this, we have 48% of free base, that's 52% of the ionized. That has to lose its ionization to partition into the brain. But you have 99.5% of the bufotenin that has to be deionized to get across. So amines must be desolvated, and the intermolecular hydrogen bond compensates for that. And that's reflected by a higher log P of psilocin of 1.45 versus bufotenin 1.2, so it's more lipid soluble. And these are all experimental measures. We didn't just calculate these, we actually measured these. And the other thing that you have to realize is the mechanism of monoamine oxidase deamination involves access to the electrons on the nitrogen. And I'm not going to spend any time on this, but this is a cofactor that's necessary for the deamination. Of monoamine oxidase, you have a cofactor and you have the amine. There are two mechanisms proposed. One is a single electron transfer, one's a nucleophilic mechanism. Whatever you call it, what it means is this is the electron pair, if you can see that, that would be on the DMT. We'd have two methyls here, but it has an electron pair, and it would attack the cofactor, and you get intermediates that eventually lead to this iminium that then falls apart in water and gives you the deaminated species. If you go with this nucleophilic mechanism, you have both electrons attacking. You again have the mechanism that leads to this iminium and it breaks down. So all these things come into play, and in addition, the mechanism of monoamine oxidase involves the attack of those electrons on that cofactor, and those electrons are being hydrogen bonded by the OH of the psilocin. So this is a unique molecule. It has everything going for it to penetrate into the brain and have high lipid solubility. So that's why psilocin is active. Bufotenin is not. None of those things happen. It doesn't form that intramolecular hydrogen bond. The pK is high. It's a highly ionized. So just to give you an idea, I think you heard Chris McCurdy and other people talk about affinities. With respect to affinity, this is the concentration that gives half saturation of the receptor. So the Ki, or Kd, is a measure of affinity for various tryptamines. LSD is 0.4 nanomolar. That means 0.4 times 10 to the minus 9th molar. That's a concentration. At that concentration, 5-HT2A receptors are half saturated with this ligand. So 5-methoxy-DMT, about 8, psilocin 10. This methyl isopropyl, which for some reason got the name foxy-methoxy, 17. A diethyltryptamine, 65. DMT, 75. Methoxy diisopropyltryptamine, 5. And serotonin, 11. These are single-digit nanomolar numbers, and they're all fairly potent. DET and DMT are going up there a little bit. But these are the kind of range of affinities you see for a tryptamine that's CNS active. Low nanomolar digits for the most part. And it generally, these represent affinity, but these all turn out to be agonists, so they activate the receptor. That's the other part of it. I'm not going to talk about that, but they all activate the receptor. So that's my tryptamine review. We should get through this. So what about phenethylamines? Well, they've found samples of dried peyote in a cave in the Rio Grande that were carbon dated to 3700 BCE, so that means these are almost 6,000 years old. And the only reason the peyote was in the cave is it had some sacramental use. You don't put peyote in a cave where people are being buried. And that's got a phenethylamine, which you're all familiar with, mescaline, 3,4,5 trimethoxy-phenylethylamine. You notice kind of a pattern. For tryptamines, we have the indole nucleus. We have two rings attached together, and then again a 2-carbon piece off to the nitrogen. And this trimethoxy is characteristic of mescaline. Not a very potent compound, but the prototype. So you see this, you go, okay, this molecule we can modify. We can do lots of things. We can change these methoxys. We can change their orientation. We can do things in the side chain. So don't give a medicinal chemist this molecule. This should say alpha-beta. You can modify the alpha and beta parts of the side chain. So what can we do? Aromatic ring substitution. Do you need all 3 of the methoxys? Do they have to be in those 3 places, or can they be someplace else? Do they have to be methoxys? And this has to be a 2-carbon like the tryptamines. That's a template in nature. Neurotransmitters, these bind to neurotransmitter receptors, and these neurotransmitters are made from amino acids. And they have 2-carbon side chains. They have a carboxy here, and then it's decarboxylated. So the 2-carbon is necessary for activity. It turns out with mescaline, you can't put nitrogens on there, like dimethyltryptamine is dimethyls. You put a single methyl or dimethyl on a phenethylamine, you kill its activity. We don't know why. We still don't know why. But you can't modify it there. But you can modify the ring substituents, and you can do things to the side chain, and we've done both. And I'll give Sasha credit for making a lot of these compounds. And there were a lot of templates. These are essential oils. Sassafras, saffrol. This is the precursor for MDA, MDMA. Even if you buy methylene-doxybenzaldehyde, they made it from saffrol. Myristicin, you can see, is a template for methoxy, methylene-doxy. Sasha made a phenethylamine out of that. Here's alemicin from nutmeg, the trimethoxy. This is the basic starting material for making mescaline. Apiol from parsley oil, dill apiol from dill, alpha acerone from sweet calamus, a 2,4,5 trimethoxy. So these all give you ideas for the kinds of things you could do to that ring. These are natural products, and plants do these things. So what happens if we make a mescaline analog with some of those substitutions? So this is mescaline. The dose of the sulfate would be in the 250 to 400 milligram range. That would be for an average dose, I guess. If you move one of these methoxys over to this position, so it's a 2, 3, 4, It's inactive, and that was established back in 1936. There was a lot of interest in mescaline. You know, Arthur Hefter identified it from the peyote cactus in 1896, and Ernst Spath synthesized it in 1919. So this was a lot of early work was focused on mescaline. So they did some natural things. They moved one of these methoxys. It was inactive. You make 2,4,5-trimethoxy, also not active up to 300 milligrams. If you put things in the para position, though, that are more hydrophobic, more lipid-like, you start seeing activity. So we made escalene, this molecule here, by changing this single carbon methyl to a carbon ethyl group. We called that escalene, and it's about 10 times the potency of mescaline. We extended that out to a propyl group and called that proscaline. So we changed this single carbon to a 3-carbon chain, proscaline. It's also about 10 times the activity of mescaline. So that increased activity, and 2,4,5-trimethoxyphenethylamine was not active, but if you put a methyl in the 4 position, the position on the opposite side of the ring from the side chain, now you get something that Sasha Shulgin called a no-calorie martini. 10 to 15 milligrams orally active, quite a bit more potent than mescaline, not really a psychedelic, and it has a very kind of gentle intoxication. Put a bromine there. This compound is called 2CB. I'm sure many of you have heard of 2CB. It's also orally active at 8 to 10 milligrams. And so if you extend this out to other things, iodine, 2CI, put a sulfur there with a methyl thiol or something, you get a whole series of compounds called the CT series. And they're all orally active, mescaline analogs, but with a hydrophobic substituent here, a more lipid-like substituent here, and this methoxy at the 3 position moved over to the 2 position. Now you can also put an alpha methyl on here like you can do with amphetamine, and if you do that, you get activity in things that are not active in the phenethylamines. So here are some affinities, again at the 5-HT2A receptor. You see, I talked about single-digit affinities. Mescaline affinity is about 1,500 nanomolar, 1.5 micromolar. Escalene, 600. Now this is TMA2. This compound has the 2,4,5 substitution pattern that you saw in the phenethylamine, which was inactive. But now when you make an alpha methyl, it's active. So presumably there's a deamination mechanism occurring with these depending on the substitution pattern. Mescaline itself apparently is not extensively deaminated, so it's orally active. But for simple phenethylamines, unless they have this hydrophobic substituent, they are. So there's something about monoamine oxidase that doesn't tolerate these hydrophobic substituents. So here's DOM, STP, first unleashed on the world in 1967 in Haight-Ashbury. Overdosed a lot of people with 25 milligram tablets. 6 nanomolar affinity for the 5-HT2A receptor. DOB, a compound that I made when I was a graduate student, Sasha made it about the same time, 0.7 nanomolar, a potent compound. It's got a bromine here, again the alpha methyl. Aleph-2, it's got a sulfur here, and again, 2-carbon chain. 2,5-dimethoxyamphetamine, which is the 2,5-dimethoxy, is not active, at least not at reasonable doses. But add on something to the pair position, and you get activity, DOB, DOM. 2CB, 0.9 nanomolar, 2CT2, 0.8 nanomolar. And then compounds that we made in attempts to find out how these molecules were binding. This compound, TCB2, 0.7 nanomolar, is a potent psychedelic. It's commercially available from Tokris, and I'll talk about that later on. And then a bromofly. That's a compound that also appeared as a research chemical, a quite potent compound, 0.3 nanomolar. So this is really getting potent. And these all started by manipulating the structure of mescaline. Again, don't you guys give a synthetic chemist biologically active compounds. So some years ago, I got a snail mail letter, this is in the days before email, from a guy named Miroslav Trampota, who was in Czechoslovakia. And he said, you know, I made this compound, and it was quite active. Well, I thought, that's interesting. Because if you look at the 2 methoxy groups, if this is DOM, this is a methyl, and these are methyls, this is a dimethoxy methyl, those methoxys can twist around. They're relatively freely available to rotate, so I've tried to show that here, so they can swing around. So what Miroslav had done was taken this methoxy and tied it into the 4-position methyl of DOM. He said it was active. So I had a student named Andy Hoffman who was working this project. So we made that. We called it Andy's benzofuran. And DOM in a drug discrimination assay, this is another one of those Greek symbols, micromoles, should be micro there, micromoles per kilogram. 0.9 micromoles per kilogram in this rat assay we used. And Andy's benzofuran was only 7. It was much less active, about 7-fold, 8-fold less potent than DOM. So I thought, well, this doesn't sound very interesting. So the question became, well, what does the orientation of these methoxys have to be to interact with the receptor? So we twisted it around and turned it and hooked this methoxy into this position. So just imagine we took this, added carbon, and hooked it in this position and made a furan. And Scott Snyder did this work, so this was called Scott's benzofuran. And what you see is Scott's benzofuran is actually a little more potent than DOM, 0.6 versus 0.9. So it takes less to have an effect, so it was more active. So if 1 was good, maybe 2 is better. So we made bromofly, and the ED50 in this assay was 10-fold more potent than SBF, 0.06 micromoles per kilogram. So this is really an active compound. And I'll say a little bit more about that later on. So we established these methoxys when they bind to the receptor. Probably this one's turned up this way, and this one's probably turned down this way, because those oxygen atoms have electrons that interact with amino acid residues in the receptor. And so they have to be oriented in a particular way so those electrons on the oxygens can interact with the serine or threonine amino acid. Well, then the question became, well, how far can you take this silly notion? So you can convert these furans into pyrans. I had a student named Aaron Monty who worked these out. This is a dipyrano compound, but its ED50 wasn't very great. 1.2 was less potent than DOM. And so then we looked at the furan in the 5 and the pyran in the 2, or the pyran in the 5 and the furan at the 2. And it turns out this one is the most potent. And so what that told us was you have to have the right orientation, but within the receptor, there's not much tolerance for a big piece of molecule here. It doesn't tolerate it here, but if it's a 5-membered ring, it does. So we've determined the orientation of these methoxys when this flexible molecule binds, and also that wherever this thing binds in the receptor, there isn't much tolerance for steric bulk or molecular bulk around it. And just to show you some of the efficacy on these compounds, here's DOB, and it has an affinity of about 1 nanomolar in this assay. And its ability to activate phospholipase C, which is one of the signaling pathways that's coupled to the 5-HT2A receptor, the concentration to activate that pathway to 50% of the maximal is 35 nanomolar, 35 times 10 to the minus 9th molar. When we lock both of those methoxys into furan rings, the affinity about doubles. We go down to about 0.5 nanomolar. And now the EC50 goes from 35 down to 8. It's about fourfold more potent at activating the receptor. And then I had a student named Matt Parker who said, you know, we could put double bonds in here and make this whole thing really 1-3 aromatic rings all planar. And that's called bromo dragonfly. Another compound that escaped from the lab and actually killed people because it was so potent. The Ki here is 0.04 nanomolar. Its ability to activate phospholipase C, the EC50, is 3 nanomolar. And when we ran assays in rats, it had twice the potency of LSD in our rats. So this was a really potent compound. I think we've really optimized what the receptor is looking for in terms of a phenethylamine, but I wouldn't say these are really ideal. This is a really toxic molecule. This is a long-acting molecule. But we've defined the nature of that receptor site, what it's looking for with the phenethylamine. We've never had a crystal structure yet, so we don't really know how it binds, but hopefully that'll come. So the other thing we did, we made a lot of what I'll call rigid analogs. So the phenethylamines have a floppy side chain. So when it binds to the receptor, there were ideas that it bound like it was completely flat, like LSD is a completely flat molecule. So we thought, well, does it bind when it's completely flat, or is it in some other orientation? So here's the side chain, and it's out of plane, in a plane like that. And we made a bunch of analogs where we tethered that. So this is a cyclopropane ring, we made a cyclobutane ring, we made aminomethyl. We made a whole bunch of different derivatives trying to map that out, because in medicinal chemistry, if you make a rigid analog and it recapitulates the activity of the flexible molecule, you can infer that it binds like the flexible molecule. So we came up with this one, TCB2, which I've mentioned earlier. This is a rigid molecule that has the side chain permanently locked out of plane. So the plane of this aromatic ring here with the methoxys, if you imagine, is flat. The side chain is in a plane basically perpendicular to the plane of the ring. And this really proved that they couldn't bind in an orientation like LSD. We got a crystal structure of that, and then we made these N-BOM compounds which have come out, which we worked on in our lab, these N-methoxybenzyl. We got a crystal structure of the active compound that we synthesized, which was an analog of the N-BOM, and it had an orientation like that. And if you look at this, here's the aromatic ring. Here are the 2 carbons going out to the amine in the side chain, and of course it's got all this other garbage attached to it. But there's the side chain, the 2 carbon to the nitrogen. Here's the 2 carbons to the nitrogen. So if you superimpose these, what you come up with is sort of a consensus structure. They bind, phenethylamines bind to the receptor in such a way that the side chain is probably out of plane if we use those 2 crystal structures by about 60 degrees. We have an amine binding site. That's pretty well understood to be an aspartate in helix 3 of the 5-HT2A receptor. There's also a hydrogen bonding site for this 5-oxygen, which we think from mutagenesis studies we identified as in helix 5. It's called 5.42. We don't know where the 2-oxygen binds. And there's probably some hydrophobic region because we know if you put iodine, bromine, things like that, they're more active. So this is sort of a consensus picture of how they bind. We did a lot of work mutating the receptor, and we had a whole library of these compounds that we put in, tried to figure out what's the actual receptor residues. We never could figure that out. I'm still hoping we may get a crystal structure of that. So that's the phenethylamines. So now I'm going to talk about a more interesting compound, perhaps. So sources of ergolines. And there are lots of people who recognize this right away. This is ergot infecting grain. And so we have the ergot alkaloids as natural templates. So for ergot alkaloids, if you take off these R groups, the amide-type ergot alkaloids, ergotamine and so forth, are attached to peptide moieties, cyclic peptide moieties up here. There are some simpler ones, but basically there's a whole family of ergot alkaloids that are of the imides. And there's chanoclavines and other things that don't have the imide, but these are the interesting ones. And these ergot alkaloids have been known for a long time, all the way back into the Middle Ages. So Claviceps purpurea and rye, these are the sclerotia, which are the dormant form of the fungus. After they grow, they become dormant, and then under conditions where they can grow again, here's one of those sclerotia, which is actually sprouted out the fruiting bodies. So although these ergot sclerotia don't look like fungi in the typical sense, given a chance, they'll sprout out and look just like typical mushrooms, toxic mushrooms. Claviceps grows on a lot of different pasturages, tall fescue, Claviceps paspale on Dallas grass. And in years gone by, bread made with ergot infected grain would lead to ergotism. So during the Middle Ages, an epidemic of ergotism killed more than 40,000 people because these ergot alkaloids are really toxic. And the natural ergot alkaloids produce vasoconstriction. They constrict the blood vessels in your fingers and toes. If you've ever seen gangrene, this is what it looks like, fingers and toes. It constricts them for a long time. The tissue becomes anoxic, necrotic, and turns black and dies. So people with ergotism, if they survive the ergotism, would be having stumps of fingers and stumps of toes. Here's a picture showing someone who's eaten some infected bread and has ergotism. Gangrene of the extremities, nervous spasms, burning sensations, hallucinations, and temporary insanity. There's actually a woman who did her PhD thesis in psychology suggesting that the Salem witch trials were related to weather such that the grain that year had a lot of ergot in it. And a lot of the people in Salem were suffering from ergot poisoning and having hallucinations. It's certainly possible. Hallucinations, and this burning, this is the gangrene in the extremities felt like their fingers and toes were on fire. This was called St. Anthony's fire. And St. Anthony was the patron saint of people who suffered from ergotism, which in the Middle Ages was common. They didn't understand you had to go through and pick all these black sclerotia out and get them out. They just ground it up and made the bread. So it was really a problem. Now, ergolines also occur in other species. Here's Ololuiki, if I pronounced that right, Turbina corymbosa. It was used by the Aztecs, I believe, when the mushrooms weren't fruiting and weren't around. The seeds contain lysergic acid amide, or ergine. This is Hawaiian baby wood rose. They have great big seeds. They actually have more ergine than these do. Morning glories, heavenly blue morning glories, Ribia cormbosa, I think. And when I was going to college, when I found out about morning glory seeds, we went over and bought a couple ounces from the seed store, and I bought them for somebody else. And then he wanted some more, and I went back a month later, and all the seeds had this pink antifungal stuff on them. So what happened to these morning glory seeds? Oh, that's an antifungal agent we put on to keep them from getting infected with fungi. When in fact the seed companies knew that people were grinding the seeds up and taking them to get high, so they put that on to make them bitter and make people throw up so they wouldn't use them. Lysergic acid amide is weakly psychoactive. So LSD, a tenth of a milligram, is quite potent. Ergine, a milligram, 2 milligrams, and it doesn't recapitulate the effect of LSD, but it's psychoactive. So you grind up the seeds of Turbina crombosa or Hawaiian baby wood rose, and they do have lysergic acid amide in there. Now, whenever I talk about LSD, I like to present this slide because a lot of people don't know this. LSD was an amazing molecule, amazing discovery. We know, I mean, we're still talking about it how many years later. It really changed the world, and I contend that if LSD had never been discovered, well, we wouldn't be here, for one thing, probably. We'd be someplace else. But I contend the world would look very different. Art, music, I mean, think about all the art and music that was sprouted in response to LSD. So it's an important molecule, but it has another importance that most people don't realize. In the 1940s and earlier, if you had a child that was schizophrenic or suffered from a major psychiatric disorder, psychiatry in that era blamed the parents. So you had mothers called refrigerator mothers. You didn't nurture your child. You didn't breastfeed the child properly. You were cold to your child. It's your fault your child is sick. That's what they thought. That's what psychiatry was telling people, majority of psychiatrists, at least in the US. So mental illness was related to bad parenting. 1943 was when Albert Hofmann discovered the effects of LSD. What happened 10 years later? We had serotonin discovered in the central nervous system. Prior to 1953, everyone believed that all the serotonin in the body was in the gut, in enterochromaffin cells. And in fact, 90 to 95% of the serotonin in the body is in the gut. So a woman named Betty Twarog went to Irwin Page's lab at the Cleveland Clinic, and she had developed an exquisitely sensitive assay for measuring serotonin using a contractile muscle from an edible muscle called a quahog. And I don't know what a quahog is, but anyway, it had a contractile muscle. If you tie a thread on each end of that muscle and hang it up in an organ bath, and you put serotonin in, it contracts. And you can hook up an apparatus to measure the strength of that contraction. And the more serotonin you put in, the stronger that contraction is. So she went to Irwin Page's lab, and she said, I'd like to analyze mammalian tissue for the presence of serotonin. So he said, that sounds like a good idea, go ahead and do it. And then she said, I want to analyze the brain to see if there's serotonin there. And Irwin Page poo-pooed her. He said, there's no serotonin in the brain, it's all in the gut. You're not going to find any. But she prevailed, and she analyzed cow brain, mammalian brain, sure enough found serotonin. Well, you may not be chemists in here, but if you compare serotonin with the structure of LSD, there are some similarities. Would you agree? So by 1954 and thereafter, there were quickly hypotheses developed that the effects of LSD were related to the blockade of serotonin in the brain, and later, a year later, were related to activation of serotonin systems in the brain. And suddenly, people thought, maybe neurochemistry has something to do with behavior. Now, today, we take that as a given, but in the early 1950s or earlier, they weren't aware of that. So LSD really catalyzed, was part of the catalysis to start this whole revolution of looking at brain neurochemistry. Chlorpromazine was introduced around 1952 or about the same time. It eventually came over. But LSD catalyzed this understanding. It was such a potent compound, and it had CNS effects, and it had this template that looked like serotonin built within the structure. So obviously there was something with serotonin. And I've gone back and looked at the National Library of Medicine, searched on serotonin those early years. And up until 1954, 55, all you see are publications talking about serotonin in the gut, the role of intrachromaffin cells, serotonin in platelets and blood serum. You don't see anything in the brain. And then a couple years after this, you start seeing papers appear, and then they rapidly escalate in publication rate. This really began the revolution in looking at serotonin in the brain, which led to, whether for good or bad, SSRIs, triptans for migraines. All the serotonergic drugs that work in the brain probably would not have been discovered nearly as quickly had LSD not been discovered. So a lot of people don't know the importance of LSD from that perspective, so you know it. Now, how can you modify LSD? Almost no one had worked with lysergamides since really Hoffman back in Sandoz. A few other people had. And the reason is this is a difficult molecule to synthesize. If you want to talk about modifying it, modify over here, forget it. You can modify this, nobody had done much of that, and you could certainly modify things up here. So when Albert Hoffman was at Sandoz, I don't know how many lysergic acid amides he made, at least 57 because it was an LSM 57, LSD was 25, so at least he gave it a code for representing its name and then a number. So we know he made probably at least 57 and probably more, and looked at all these, and none of them had activity like the diethyl. And we synthesized a library probably of 25 of those in our lab and looked at their activity. Nothing approaches the potency of LSD. Those diethyl groups are really special. We've made all kinds of things up here. And then nitrogen here, the N-methyl that you see in the natural ergolines, we plucked that off. Some Japanese people had published on some substitutions, so we followed their procedure. We put ethyl, propyl, butyl, allyl, a whole bunch of things here, and actually came up with compounds that were more potent than LSD, and I'll talk about those in a minute. So with respect to that as a template, you can modify here, doesn't get you very far. Modify here, you get some interesting compounds, and you can't put things over here. In fact, the synthesis of lysergic acid, the total synthesis of lysergic acid for natural products chemists was kind of Mount Everest. You really cut your chops if you could do a total synthesis of lysergic acid. Kornfeld's synthesis in 1956 was a tour de force. It took up many pages in the Journal of the American Chemical Society, and that was kind of a classic. And there have been many syntheses published since then, but none of them are practical on a preparative scale. The best way to get these compounds is still from ergot fermentation, submerged fermentation. So, this is the slide, Dennis. Okay, we'll see. I'm gonna So how did we test these molecules? From the time I started my graduate work in 1969, I did my graduate study on psychoactive and then continued on all the way through to the present. We had to use animal models, despite the fact that I had uncounted numbers of graduate students that volunteered to test my compounds. So we learn about physiology by using drugs that perturb physiological systems. So if you want to know what the beta-1 receptor does in the heart, you give a beta-1 agonist, and you see it speeds up heart rate. You give a beta-1 antagonist, slows heart rate. So if we want to study consciousness, wouldn't it make sense to use compounds that perturb consciousness? And that's the basic driving hypothesis of what we tried to do to generate tools that we could use to study consciousness, to perturb brain function. Now, this may or may not work. Let's see. This is Sasha. Many of you knew Sasha Shogun, or was at least aware of him. So, you know, the way he tested things, he made them himself and tested them small doses and up to a point where he either found something or he didn't. And then his wife, Ann, he'd go to Ann and say, Ann, I got a really interesting compound. It was active at 25 milligrams, and, you know, I think 10 milligrams for you will start. And so then she'd try it, and oh, Sasha, this is a marvelous compound. So, so they had a whole bunch of people that were professional people, functional people with jobs. They weren't hippies. And so every now and then, they'd all meet at one person's house, and Sasha would say, I've got a new molecule, Ann and I have tried it, and we think it's really interesting, and we'd like you all to try it. And so then the group would try it. Now, those of you that have PCAL or TCAL, he has in there the doses that were given, the dose ranges, and some descriptions for each one. He could do that, but I couldn't. But his work was really important because if we had an animal model of hallucinogenic activity, how would we know it was valid or not? Oh, well, Sasha tested it in humans for the ones we had. Let's go look and see if it was active in humans, and then it was active in our rat model. It would be some validation that our model was at least correlative, if not predictive. And how did we do that? Now, don't anybody laugh. So we used a procedure called drug discrimination. I'm going to explain. I have enough time to explain this carefully. So this is an operant chamber, and it has 2 levers in it. You start out with a chamber with only 1 lever, and you have that lever so that if a rat presses it, it delivers a 50 milligram sucrose pellet. It's a 50 milligram rat candy. Now in the wild, rats don't press a lever. So you first have to teach them how to press a lever. It's called shaping. So you put the rat in here, and rats, like all rodents, are very exploratory. They'll go all around. He'll stand up on these bars. He'll sniff up to see what's happened. If he stands on that bar, there's a click because there's a solenoid that delivers that. And then his food pellet comes down. He sticks his nose in there. Yum, yum, rat candy. So he wanders around some more. He steps on it again. Bang, another food pellet. Pretty soon he learns that whenever there's one of those levers sticking out, if I step on it, I hear a click and I get a candy reward. So then we kind of play trickster with him. Not quite like Schultes was a trickster, but anyway. We put 2 levers in. And now we say, okay, we're only going to activate the lever when we give the rat a drug. So let's give this rat LSD, an injection. We do it intraperitoneally. We gave 80 micrograms per kilogram, which is a low dose for a rat. You don't see any other behavioral effects. This is a really sensitive assay. We put the rat in here and we turn on the right lever, but we don't turn on the left lever. So the rat comes in, he sees these levers. He knows if I press this lever, I'm going to get something. He presses the left lever, nothing happens. He presses the right lever, he gets a food pellet. Oh, okay. So he starts doing that. It takes him a while to understand that only the right lever is working, but he starts to understand it. So then we take him out, 15-minute training period. The next day we put him in, we give him a placebo saline injection. We turn on the left lever, we don't turn on the right lever. So now he goes in, he presses the right lever, nothing happens. He presses the left lever, food pellets. So over a period of 2 to 3 months, it takes that long, the rat will reliably learn that if we give him LSD, he only presses this lever and he gets food pellets. If we give him placebo, he only presses this lever. Now this is a powerful assay. It'll detect any centrally active compound. You can use amphetamine, MDMA, we've done those, all those. And at doses below those that produce any overt behavior. So the rat doesn't look any different at all. People have asked me if our rats are hallucinating. I said, I have no idea. Anyway, so after he learns this, and this is a robust assay. The other thing is there's something called a third state hypothesis. If we've trained this rat to respond to the injection of LSD and we give him amphetamine, he responds on the placebo lever. If we give him MDMA, he responds on the placebo lever. He only responds on the drug-associated lever if the drug we give him was like the training drug, in this case LSD. So say we made some analog of LSD, we gave it to the rat, we put him in here, he's trained to press on the right lever, so he says, I think you gave me LSD. Now, that is not much of an assay if you know what LSD normally does to humans, right? But it's the best we could do. And we actually have shown that the potency and drug discrimination in LSD trained rats parallels really nicely human doses. So it's a good assay. So here's some of those compounds we made. So here's the diethyl group, and we replaced the methyl of LSD, took it off completely, or put in ethyl or propyl, allyl, isopropyl, butyl, phenethyl. FLAD and ALLAD both are research chemicals now. You can buy them on the internet. So here's the potency of LSD. We set it as equal to 1. The FLAD, the potency is 2.3. ProLAD, 1.2. ALLAD, 3.5. In rat assays, these compounds are all more potent than LSD. In humans, the ethyl is probably the most potent. But we see a general parallel with what happened in humans. And I can't tell you about any lab assays we did on any of these others, but I can tell you they parallel the rat potency. So if you extend out that group to a butyl, activity drops way off. An isopropyl, you branch it, activity drops off. A phenethyl here, sometimes gives active compounds when you have opiate-type activity, and that compound is inactive. So ED50 is from LSD-trained rats in that drug discrimination paradigm, and that's what we use for most of our studies. There's another assay, and this one is even sillier, so don't laugh. But I didn't develop it. It's called the mouse head twitch. So when we started working with rats, they cost about $2 a piece. White rats, white laboratory rats. And I understand now they're like $50 a piece. Or I don't know, are they more than that? About 50 a piece. Plus you have the per diem charges to keep them, and those went up too. So if you have a big rat colony, it's really expensive. And we had rats trained to MDMA, amphetamine, LSD, and maybe some other things. So we always had like 100 rats, and we're paying all this per diem, so it's expensive. Well, somebody found out if you give a psychedelic to a mouse, he shakes his head, he twitches his head. 90 hertz. 90 hertz, and it's fast. And the way you typically would do it is inject the mouse, put him in this chamber, and have a video camera, video the whole thing, and then play it back in slow motion and look for him to do this head twitch, and then score it. That's not very high throughput. So Adam Halberstadt, a colleague of mine who worked in Mark Geyer's lab, came up with a really good idea. He took a magnet, a really high Tesla little magnet, one of these things that you stick on the refrigerator you can't get back off, opened up the skull, glued that magnet with bone cement to the skull, opened the scalp, glued it to the skull of the rat. He's under anesthesia, he doesn't feel anything. Suture him back up, put some antibiotic in there. He's fine, he's happy. The magnetic field doesn't bother him. Once he heals up, Adam put him in a glass tube with copper wire wound around it. So when he shakes his head with that strong magnet and the field goes through the copper wire, it generates a current. And you can filter that out. This is the head twitch, the actual unfiltered head twitch. This is what it looks like. And you can do it high throughput. You can have 10 of these mice or 20 of these mice. You don't have to train them like you do in drug discrimination. So that saves money. Mice are cheap. They're about probably what rats used to cost. And you can filter out. So here's an injection vehicle, like one twitch over this whole time period. 0.5 milligram per kilogram, you see twitches, 1 milligram, 0.5 milligram, 1 milligram, and you can quantitate these. So it makes it really easy. Here's LSD in that head twitch assay, dose response from 50 to 100 to 200 to 400 micrograms per kilogram, and you see you get a nice increase in head twitches. Now, this is what you're forced to work with in academia when you really wish you could have some humans to come in and say, you know, we'd really like you to try this. Drug discrimination, which is expensive and fewer people using it, costs a lot, you have to train them. Or this mouse head twitch where there's a couple labs using it and you get this correlation. So it speeds it up, but it's really a very poor echo of what you wish you could see in a model. So we asked the question, why is the diethyl group so important? If you change the diethyl amide on LSD to anything else, activity drops off by typically an order of magnitude. So methyl, propyl, dimethyl, dipropyl, ethyl propyl, all kinds of things, activity typically drops off. The only molecule we ever found that had activity even close was a methyl isopropyl, and it was about 1/3 the activity of LSD, but everything else about an order of magnitude gone. So I had a student who said, let's look at the stereochemistry of this position. So this is a 4-carbon piece, so it has the same number of carbons that you have in the diethyl, but it's hooked at the 2 position, and because it's asymmetric, you have an R and an S enantiomer. When we tested those in drug discrimination, LSD was 25 nanomoles per kilogram for an ED50. This was 33. It was the same potency. This one was 4-fold lower. If you tie it into a ring, it was even less potent. So this said, you know, wherever that diethyl amide is binding in the receptor, there's some kind of chiral discrimination. It's looking for a particular stereoisomer. How could we test that and find out? So the way we came up with, and we published this in 2002, was to lock those diethyl groups into the formation of a 4-membered ring. So if you take this carbon and you hook them together with another carbon, you get a 4-membered ring. So here's the diethyl groups essentially over here. And the thing that happens when you do that is you have 3 possible isomers. Those 2 methyl groups can be on the same side of that 4-membered ring. They can be on the opposite sides this way, or they can be on the opposite sides this way. So we've locked it in so that the ethyl groups can't move around like they do here. They have to stay in that fixed conformation. So here's two conformations of those ethyl groups. The front ethyl pointing down, the back one up in the back, the front one up and the back one down. And here are two of these isomers, one designated SS. You can see the similarity in terms of this position of this methyl and this one compared with the freely rotating LSD. And here's the top view. Again, you can see the similarity. So which one of these is active? This one, the SS. And this is actually a research chemical on the market called LSZ. So people watch the stuff we publish. So that showed us clearly that when those diethyl groups bound, there was a very specific orientation. It didn't just bind in a flexible way. The receptor was looking for a specific orientation. And here's the ED50 in drug discrimination. Here's LSD. Here's the SS compound, really more potent than LSD. Here was the cis with the methyls on the both side of that ring. And here was the RR, much less potent. So these were the azetidides. So we had established the stereochemistry of the diethyl groups. And we did some virtual docking, which means computer representations of what we thought happened. We built a model of the 5-HT2A receptor. We docked LSD in there. And what we noticed was there was a piece of the receptor that connected the top of helix 4 to the top of helix 5. And there was a leucine 229 that looked like it was right there next to the diethyl groups. Now, I don't know if you know much about GPCRs, but there are 7 transmembrane helices packed together. And so they go in the top, up the bottom, in the top. So there are loops that connect the top and the bottom. This was the loop that connected the top of helix 4 to the top of helix 5. So my last student, John McCorvey, what we did is mutate. There's 229 was the second residue. We had 228 and 230. In the wild-type receptor, it's a leucine, and an alanine. We mutated those to valine, serine, isoleucine, and asparagine. And if you look at the effects on affinity, without trying to analyze this, basically what we found was the mutations had a similar effect to the SS as it had to LSD. So that was the most similar. And again, it looked like 229 was an important amino acid residue. So in January, we published the crystal structure of LSD and the serotonin 2B receptor. The first time LSD has been published in a crystal form of any receptor. And this is a rendering, a van der Waals rendering of what that receptor looks like from the top, from outside the cell, looking in. These all have the hydrogens. I'm just showing them as gray. Here's that extracellular loop 2, leucine 229. Here's LSD in the red, peeking out from below. So here it is, and this is the loop, and you see that leucine actually bends down and kind of packs in or wedges in next to the LSD structure. Then we had Ron Droyer do molecular dynamics simulations. So molecular dynamics are a computational procedure where you essentially, through mathematics, you heat the receptor up so all the atoms are vibrating, and then you cool it down and it falls into a certain position. You do that over and over until it reaches an equilibrium point. So he did simulations with the wild type. This is the 2B receptor. And then we took the mutation. We mutated that leucine 229 to a smaller alanine. So it was much smaller. And what you see is in the unliganded wild type receptor, there's no LSD in there, or with LSD, the percent of time that that loop is open and gives access to the inside of the receptor is 1 or 2%. But when you mutate that to an alanine, a smaller residue, now it's open about 13% of the time. So, and this is flexibility. So again, the red is the alanine mutation. So we'd shown that that loop over the LSD doesn't open very often. It only opens a few percent of the time. We can just ignore this. So these are dose response curves, and I think Chris McCurdy referred to GQ, flux. So we looked at 2 signaling pathways. GQ-mediated calcium flux, which is the standard canonical signaling pathway for the 5-HT2A receptor, and then we looked at beta-2 arrestin recruitment. So if you look at the serotonin 2A receptor, the things that happen when you activate it inside the cell, there are about 9 different things that we know are turned on. It's just like it's not like an on-off switch. There are lots of different signals that are turned on. So this GQ activation was the canonical one, producing increased calcium, and beta-arrestin 2. We thought, okay, you notice if we look at that, here's LSD in the purple, the SS azetidide, which was comparable to LSD in all of our other assays. It's right here, it's purple. And the RR, which was less potent, it's over here. In the calcium flux assay. But when you look at the beta arrestin recruitment assay, LSD and the SS-azetidide are both over here, but the RR is shifted to the right. So this is telling us with respect to arrestin recruitment, the SS, azetidide, and LSD are doing the same thing, producing arrestin. There's no difference between the isomers, the R and SS azetidide, if we look at the canonical GQ signaling. But there is when we look at beta arrestin. So then, John McCorby, who's doing a postdoc, he was my last grad student, he's a postdoc in Brian's lab. He did receptor kinetics. And so this is going back to the 5-HT2A wild type. So you incubate the receptor with tritiated LSD until it's reached equilibrium. And then you wash that off, put fresh buffer in, and you see how long it takes the LSD to come back out of the receptor. So the wild type receptor is this curve right here. And this is 600 minutes, 10 hours, before it really gets back down to baseline, 37 degrees centigrade. If you mutate that leucine 229 to an alanine, increasing the flexibility of that loop that's locked LSD in, now look what happens. Boom, it comes out and here's 240 minutes, 4 hours. So there's a very different kinetics off rate for LSD in the wild type versus the mutated receptor. Again, if you look at calcium flux in the wild type versus the mutant receptor, you don't see any difference. Calcium flux doesn't care how long the LSD is locked in there. But with respect to beta arrestin recruitment, when you do that mutation, you lose that arrestin recruitment. So arrestin is a molecule that has a lot of signaling properties. It's also responsible for internalization of the 5-HT2A receptor. We know that LSD causes a receptor to become desensitized or internalized. We also think we've got studies that are unpublished that indicate that this arrestin recruitment is also related to some of the behavioral effects of LSD. So what we basically can say is when LSD gets inside the receptor, it takes a while to get in, but once it gets in, it takes a long while to get back out. And while it's stuck in there, that prolonged being embedded in the receptor for a long time leads to recruitment of arrestin signaling, and that arrestin signaling we believe is related to some of the psychoactive effects of LSD. So the big question, so this is a crystal structure of LSD in the serotonin 2B receptor. And this is from this paper, Wacker et al. 2017, January, published in Cell. So the question was, we predicted, this is the conformation that's actually in the crystal structure. We predicted with those azetidides a particular conformation. Does that agree with what we found experimentally? So we published that in 2002, this is 2017, so that's 15 years. And indeed, when we superimpose the SS-azetidide on the crystal structure, it essentially superimposes. The R-azetidide would have this blue, would be over here, and would be down here. So we predicted in 2002 with those rigid analogs the conformation of LSD when it bound in the receptor. And this diethyl group is really important, and the receptor, the loop, folds it in and holds it in. Probably these other analogs, lysergic acid, dimethylamide, and things like that, they just don't get trapped in. It's unique to the structure of LSD in that diethyl group. So I sometimes say it's kind of curious that that receptor has evolved to be exactly complementary to the structure of LSD per se. So I should acknowledge I didn't do this work all myself. I had 45 graduate students, 31 postdocs, and visiting scholars. And for 29 years, my work was funded by the National Institute on Drug Abuse, believe it or not. So with that, I'm finished. I hope I kept everybody awake. I finished on time. Thank you very much.